Hi class, we're on to chapter 3.2, Matrix Algebra. So in this section we are going to discuss how to do algebra of matrices, adding them, multiplying them by a scalar, things like that. So we talked about matrices just a little bit in the previous section on linear transformations. So we're really going to extend this idea. We are going to talk about linear transformations just a little bit more. But now we're going to take those matrices that we've been using as a linear transform and learn how to do algebra on those, right? So first, let's talk about addition and subtraction. We'll also introduce some new notation for matrices. So in order to add or subtract matrices, they have to have the same dimension, okay? Meaning they have to have the exact same number of rows and the exact same number of columns. If they do not match up dimension-wise, then they cannot be added or subtracted, okay? When we add matrices, so for the time being, I'm only going to talk about addition because subtraction is just a form of addition, right? Subtraction is just adding together a negative value. So I'm really only going to talk about it in the lens of addition, because all you're going to do is change the signs for a subtraction, okay? So if you want to add two matrices, it's actually very, very easy. You're just adding the components together, right? So the elements in the upper right corners of both matrices add together. The elements in the third row, second column add together, right? So each component adds with its pair in the other matrix that you are using to add together, right? So in general, some slightly new notation. If I want to add or subtract two matrices together, this is a secondary notation for a matrix, A sub ij, where I is the row and j is the column entries, okay? So remember, rows, columns. So A sub ij, I is the specific row that you are on, and J is the specific column that you are on. So it's basically saying that the entries in each row and column add or subtract with the paired row and column. Okay, so if I'm adding two matrices, okay, it's the same thing if I'm just adding or subtracting their components together, right? So for instance, if this is my matrix A, this is another way of representing a matrix. It's actually probably the more common manner of this. So remember that the subscripts are the entries. This is the element in the first row, first column. This is the element in the nth row, second column. This is the element in the second row, mth column, right? So this matrix has n rows and m columns, right? So if I take this, in order to add it with another matrix, the matrix B also has to have n rows and m columns, okay? And so when I add these together, I'm literally adding them component-wise. So this entry and this entry add together, this entry and this entry add together, and so forth throughout all of the terms. Okay, so that's what it looks like to add two matrices together. You're taking all of their respective components and you're adding the respective components together piecewise or component-wise. Okay, so let's do a brief example. If I have this 2 by 3 subtracted by this 2 by 3, I'm just taking each term and subtracting them. 1 minus 6 will give me a negative 5. 2 minus 5 will be a minus 3. 3 minus 4 will be a negative 1. Right? Minus 5, minus 3, negative 1. Same thing here. 4 minus 3, 5 minus 2, 6 minus 1 is 5. So each component just gets added or subtracted to its respective component in the second matrix. Scalar multiplication, right? So one thing to bring up, this is very, very similar to adding vectors together, right? And when you add two vectors, their components add together as well. Scalar multiplication is also very similar to a scalar multiple of a vector, okay? Scalars multiply your matrices component-wise. So if you have a scalar multiple of a matrix, every entry in that matrix gets multiplied by that scalar. Okay, so in general, if I have a scalar value, right, C is a real value, then C times A, C times my matrix, is the same as C times this form of the matrix notation, which means that each term inside of there gets multiplied by that C. So in the secondary notation, right, we have our scalar times our entire matrix. That's just going to be all of these entries multiplied by that scalar. Okay, so that scalar comes and it multiplies every single entry in that matrix by that value. Okay, so an example, if my matrix is 1, 2, 3, 4, 5, 6, and I multiply it by 2, everything in this matrix gets multiplied by 2. Okay, very, very straightforward to add and multiply matrices by a scalar. So here's another theorem. Let's say we have two scalars, S and T, and we have three matrices that are all n by m. So all three of these matrices have n rows and m columns. Okay, and let this be the zero matrix. So the zero matrix is the matrix made completely of zeros. There are no other entries except for zeros. And this subscript here is telling you that the zero matrix is also n by m. It has n rows and m columns. Okay. Often we do not write the n by m subscript on the zero matrix. Okay. So normally we just say let zero be the zero matrix, and then we just fit it to our needs as need be. We typically don't need to specify the dimensions, but if you want to be very, very rigorous, then you are specifying the dimensions, like inside of a theorem. You would specify this, but when you're doing your math, you don't have to say, this is the 0, 3 by 2 zero matrix. We don't have to do that. You just say the zero matrix, and then, you know, the reader should be able to figure out what the dimensions are, or you'll write the actual zero matrix. Okay, so it's not important to write the subscript here. Only if you're being very, very formulaic. Okay, so we have some properties of matrices. Okay, so if I want to add two matrices together, they commute under addition. So that means that A plus B is the same as B plus A. It doesn't matter which order I add them in. Okay, that's not true for everything that we do here, but that is true for matrices, for addition. If I multiply the addition, the sum of A plus B by a scalar, it's the same as if I were to distribute that scalar across both matrices and then add them together, right? So S times the sum of A plus B is the same as the sum of S times A plus S times B. If I have two scalars that I'm adding together and multiplying that times my matrix A, it's the same thing as if I were to distribute this A across my scalars. Okay. If I have A plus B plus C, it does not matter which one I decide to add together first. Okay. So this is the associative property of matrix addition. So I can add A and B together first and then C, or I can add B and C together first and then add A. Okay. If I have a scalar S and T times A, it doesn't matter which order I multiply these. I can multiply these together first as a single scalar and then distribute it across the entries in A, or I can multiply A times T and then multiply it by S, and I should get the same thing. Okay. And for the last one, this zero matrix acts as the additive identity for matrices, meaning that if I add A together with the zero matrix, I'm adding all of the entries of A plus 0, which doesn't change anything. So I'm just going to get out my matrix A. Okay, now let's talk about matrix multiplication. Now this is much more difficult. I alluded to matrix multiplication a little bit in the last video, when we were talking about transforming, using a vector times our transformation matrix. So that kind of sets up how matrix multiplication works. A lot of times it's very, very difficult for students to grasp when they first see it. It takes you some time to get used to, but we're going to do it for the rest of the semester, so you'll get used to it. Definitely want to practice it. Don't just look at it and be like, oh yeah, I know how to do this. You definitely want to practice this thing a few times. You want to be able to get really, really good at it. So for instance, when I do matrix multiplication, I generally don't have to write anything down. I can just be like, oh, it's this value, this value, this value, this value, right? So you definitely want to get good at doing this, because the better you are at multiplying matrices, the easier the rest of the course is going to go for you, okay? So for matrices to be able to multiply, their dimensions have to match up, okay? So when I say their dimensions have to match up, it needs to be the inner dimensions need to be able to match up. So the number of columns of the first matrix has to be the same as the number of rows of the second matrix, okay? And we'll look at a way how we can check this. I mean, visually you can look at it and tell if it works or not, but there's also some things, little subscripts that we can write to help us out. Okay, so the number of columns of the first one and the number of rows of the second one have to be the exact same number. If they are not the same number, you cannot multiply them together. That is the only condition you need in order to multiply matrices, right? Is that those two numbers are the same, okay? The order in which you multiply matrices is important, okay? We'll talk about this quite a bit. There is what we call left-hand multiplication and right-hand multiplication. They are not the same, okay? So for instance, if I take two numbers, 2 times 3, I'm going to get 6. But if I swap the order, 3 times 2, you're also going to get 6. But in linear algebra, that is not true, okay? I cannot swap the order when I multiply. That is not, it is not commutative under matrix multiplication, okay? Matrices do not commute through multiplication. You cannot switch the order. I'm making a big deal of it because I do not want you to make that mistake, because it will hurt you as you do things, right? So what does that mean? It means A times B, this product does not always equal B times A. Sometimes it does, and in fact, when it does, that's a very, very special case, and we actually like those types of matrices a lot, and we have a whole branch of mathematics based around those matrices that do commute. But it's not always the case. In fact, most of the time they're not going to commute. Okay, most of the time this is true, that they are not equal to each other. Okay, so if I have a matrix that has real values, that has dimensions m by n, so m rows, n columns, and B is a matrix that has real values and has n rows and k columns. So notice, the number of columns and the number of rows are the same, so that means that I can multiply them together. And when I multiply them together, the end result is the first value, right? The first matrix's number of rows and the second matrix's number of columns is going to be the dimensions of my product. Okay, so A times B, the inner dimensions match up, right? The number of columns here, the number of rows here match up, so that when I multiply A times B, the result is the outer dimensions, right? The M and the K, right? The two outer dimensions is what the product is, and in order to multiply them together, the inner dimensions have to match up. Okay, so this is the formal way of writing this. We'll also write it in some other ways so that it makes sense. Okay. In this case, if these were my two matrices, I would not be able to even multiply these together if m and k were not the same value, right? So if this is 2 and 3 and this is 3 and 5, I could not switch b and a to multiply them, because m and k would then be the inner dimensions and they would not match up. Okay, so sometimes you can't even swap the matrices around and multiply them in the other order. Now, this is very general and very abstract, so you might be glazed over right now and be like, I don't know what the hell you're talking about, Professor Williams. So we'll look at some examples after we flesh the ideas out a little bit more, okay? Because we haven't even talked about how to multiply the matrices yet. We just talked about when it's possible or not, right? So in order to actually multiply this product together, okay, we're looking at each entry in the row of A, and we're multiplying that row vector times the coinciding column vector of B, and we're multiplying each entry together and adding them together as a sum to make a single value in the product of AB. Okay, and we do this by row and column. Okay, so we look at the rows in the first matrix and the columns in the second matrix. So for example, the entries in row 2 of A multiplied against the entries in column 3 of B will create the entry for 2, 3 in your new matrix AB. Okay, so this AB here, this is the subscript, this is the term for the value that you're going to have in the AB, right? So your AB term, 2, 3. So the entry in the second row, third column, is formed by multiplying the second row and third column of your two product matrices that you're trying to form the product from. Your factor matrices, I guess. Okay, so let's do this as an example. I'm going to do this very, very slowly. Maybe you want to replay this once or twice. Just this portion here at the 17-minute mark. Okay, so let's say we have a matrix A that looks like this, and a matrix B that looks like so. And notice that the dimensions match up. Okay, so remember, it's the inner dimensions. So the number of columns here and the number of rows here have to match up. So I have 2 columns and 2 rows, so these can multiply. My resulting matrix, AB, is going to be the outer dimensions, or the number of rows here and the number of columns here. So my end result should be 3 by 3. So this is what we're going to do. I take one row and I multiply it times entries here. That's why it has to match up. Okay, I have 2 entries, and this is 2, right? This row has 2 entries in it. This column has 2 entries in it. So I can multiply 1 times 3 and 2 times 4. I'm going to add those things together, and that's going to be my entry in the first position, because this is the first row, first column. So it makes the entry in AB 1, 1. Okay. When I take the third row times the third entry, that's going to be my very, very last entry, right? This is 3, 3. So 2 times 3 plus 2 times 3, or 12, will be the entry in the last place of my product matrix. So let's look at this. Okay. So again here, note that my dimensions are the same, right? A is 3 by 2, B is 2 by 3. The inner dimensions match. The outer dimensions, 3 and 3, is what the dimensions of my product will be. Okay, so AB will be 3 by 3. So let's actually multiply this together. Okay, AB, I have my A, I have my B. We're going to go slowly, piece by piece, so that we can see this. I'm going to go 1 times 3 plus 2 times 4. First row times first column, right? The respective entries multiply times each other, and I add the results together. And since this is the first row, first column, that product and sum will create my first entry. Okay, my next entry is going to be the first row times second column to make the entry 1, 2. 1 for first row, 2 for second column, right? So I'm going to have 1 times 4 plus 2 times 3. Right. My last entry here is going to be my first row times my third column, or 1 times 3 plus 2 times 3, right? And then I'm going to move on to the next row because now I'm going to create the next row in my product. So this row times this column is going to make the entry in the second row first column. 0, 3 plus 1 times 4. This row times this column will make the entry in the second row second column. Okay, second row second column. So 0 times 4 plus 1 times 3. And then the second row times the third column will make the entry in the product of the second row third column, or 0 times 3 plus 1 times 3. Okay. Same thing for the last one. The last row times the first column is going to make the entry in the last row first column. 2 times 3 plus 2 times 3. Oops, sorry guys, this should be 2 times 3. Oh, no, I'm sorry. It is, it's this one, 3. 2 times 3, 2 times 4. Last row, second column. Last row, second column. 2 times 4 plus 2 times 3. Then 2 times 3 times 2 times 3. Okay, and then we can add all these together, right? So generally when I do this, I'm just going to do this very quickly in my head and write the value, right? This is 3 plus 8, I would just write 11. This is 4 and 6, I would just write 10. This is 3 and 6, I would just write 9, right? You don't have to write everything out. I know that I'm kind of a stickler right now for you showing me that you know how to do everything. Matrix multiplication, once you understand the way that it works, I'm fine with you just giving me the results, okay? That does not mean that you should jump on your calculator or something on the internet and just multiplying things all willy-nilly. Because when we start having abstract values here, A's and B's, I's and things like that, and then you don't know how to multiply a matrix because you did everything on the calculator, it's really going to hurt you when you come to do the exam or finish your homework or something like that, okay? So get in the habit of struggling through how to do this, because that's how you're going to learn, right? You master through attempts, right? Through actually doing. So now when I write this actual result, okay, as I said before, 11, 10, 9, and then you just finish out everything else, okay? So if you need to write everything out, then that's fine. Do that for as long as it takes for you to get comfortable, right? So that you're not making mistakes, and that's not a problem. There's nothing wrong with writing more. I would prefer for you guys to write more than to write less. I don't care how smart you guys are, how fast you can do it. I just need to make sure you guys actually know how to do things in this class. So the more you write, the more likely you're going to get a good score in this class on an exam, okay? Which is what really matters. I know I ding you guys a lot on the classworks, but they're just classworks. They don't really mean a lot to me. I just really want to make sure you guys are practicing things, right? It's the exams that you guys are really getting prepared for. That's why I ding you and then write your comments so you can get all of this stuff fixed before it actually counts a lot towards your grade, right? So, notice here that AB is a 3 by 3 matrix, okay? Which we had called. We said that the end product would be a 3 by 3 matrix, and it was, okay? Now here I'm saying that B times A should be 2 by 2, okay? And let's look at our dimensions. Okay, if I reverse this order, notice that this is 3 by 2 and 2 by 3. So if I put B in front and A behind, the inner dimensions then are the 3s and the outer dimensions are then the 2s when I reverse the order here. So then that means that our result, if I do B times A instead of A times B as I did here, okay, will give me a 2 by 2 matrix. So that right there tells you that A times B and B times A is not going to be the same value, because A times B is 3 by 3. B times A is a completely different matrix. It doesn't even have the same size. All right, it's going to be a 2 by 2 matrix. So that right there is proof that that's not an actual proof, but that's, you know, an example that A times B is not the same as B times A. But let's go ahead and do this. So remember, the inner dimensions have to match up. The inner dimensions is 3 rows, 3 columns. That means that everything that I need to multiply here has enough stuff to multiply by, okay? Each entry here, 1, 2, 3, is going to multiply by something in here, 1, 2, 3. So instantly, if this was only 2 columns, or I'm sorry, 2 entries, right? There's this no third row here. This 3 would be left out. Okay, I would go 3 and 4, 4 and 0. This 3 would have nothing here, which is why it would be impossible to multiply. That's why the number of columns has to match the number of rows, because the number of entries in this row needs to match up with the number of entries in this column in order to do the multiplication. So here the first entry. So real quick, pause it. Okay, I want you to multiply this times this on your own, and then let's go through the work together and see if we come out with the same thing. Okay, so pause it in 1, 2, 3. Okay, hopefully you did the work and you're coming back to be able to check your work, right? We can see how your thought process differs than my thought process, or maybe you had some arithmetic errors, but this is always a good exercise to just see if you're on the right track for understanding, right? So you should get 9, 16, 10, and 17. So 343 times 102 means you're only going to multiply 3 and 6 and add them together to get 9. Here you're going to get 6, 6 plus 4, so that's 12 plus 4 is 16. Here you're going to have 4, nothing, and 6, so that's going to be a 10. 4, 3, 3, 2, 1, 2, so that's going to be 8. That's going to be 9, right? So 8 plus 9 is 17. So that's how I did it in my head. It's just a very quick multiplication and addition, right? So 9, 16, 10, 17. And it's very, very clear to see here that these are not the same matrix. Okay, AB is definitely not the same as BA. So these things do not commute. Okay, so the order that you multiply things together matter, right? So in general, for A being an M by N matrix and B being an N by K matrix, we're going to have the product being M by K. Okay, and in general, this is how we look at this, right? So it's lots and lots of sums. Hopefully you guys have finished Calculus 2, because that's a prerequisite for this course, right? So you should be familiar with the summation notation. So let's kind of break this down a little bit, okay? Remember, rows, columns, rows, columns. So subscript wise, remember all the A, IJs are from your A's. The B, IJs are from your B's. So this first entry is you multiplying everything in the first row of A and the first column of B, going one entry at a time, and as you have one entry, you multiply them and add them together. For instance, so if this was 1, you're going to take A11 and B11, A11 and B11, multiply them together, and then move on to the next element in the sum, right, which is 2. So you're going to have 2 and 2, right, A12, B12, multiply them and add them together. And you're going to move on, so forth and so forth. So I wrote this in haste because this does not go into infinity, right? This is going to go to n in this case, right? You're only going to go up to n. You're going to stop somewhere because you only have this many number of rows and columns. So all of these should be up until n. So apologies on that. I didn't even think about that until I started talking you guys through it. But these don't go to infinity. They just go till you run out of columns or rows or what have you. Okay, but this is the notation for it. Okay, so I sub n is the n by n identity matrix. So the identity matrix is the multiplicative identity. Okay, so that when you multiply, so it's like our 1, right? 1 times 3 is going to be 3. That's what this matrix does. So that when you multiply it times a matrix, you're going to come out with your same matrix. The identity matrix is very, very, very important. You guys are actually already familiar with it. I just haven't given you a name for it yet. Okay, it's a very, very important matrix. You can only have the identity matrix as a square matrix. It has to be n by n. The dimensions of the rows and the columns has to be the same. A lot of times we do not write the subscripts. Okay. More often than not, you will not see it. Again, you only kind of write the subscript when you are trying to be rigorous in your definition of something. But generally, you can figure out what the dimensions of the identity is. Okay. So what the identity is zeros everywhere except for along the main diagonal, and your entries in the main diagonal are all ones. Okay. So another way of writing that is what we call the elementary unit vectors, or the standard unit vectors. We've talked about these a little bit, but not specifically. You probably have not seen this notation unless you read the textbook in the last video is when these were brought up. But I did not have a specific notation for them, although we did talk about them. So you should be somewhat familiar with these, especially if you've been reading, then you will be familiar with these. If you're only relying on the videos, then maybe not so much. So basically what these are is E1 means that the first entry is 1, everything else is 0. Okay, so this would represent the x-axis. This would be the y-axis. The next one would be the z-axis, all the way up to n. So obviously past 3 dimensions, it doesn't make sense to have more axes because we live in a 3-dimensional world. You could argue that space and time is a 4th and or 5th dimension, yada yada yada. But in this class, we literally go up to infinite dimensions, or some finite dimension could be 100,000,003. It doesn't really matter. The methods in this class are meant to work for really almost anything. So we're going to call these, so this is how we form the identity matrix. Okay. So what does this look like? 1, zeros everywhere. The next one is, that means that there's a 1 in the second position and everything else is 0. This means that there's a 1 in the last position and everything else is 0. Okay. So your identity matrix has zeros everywhere except along the main diagonal. And along the main diagonal, every single entry is 1. That is what the identity matrix is. And as I said before, we generally do not write the subscript n. We just say I, and then you should figure out what the dimensions need to be based on the matrices that you're working with, right? So if A is n by m, then A times im. So remember, the dimensions have to match up. So this is rows, this is columns. So since this is being multiplied on the right hand side, it has to match with the inner dimension. So this has to be m by m. Okay. If I were to multiply it on the right hand side, then this is now the inner dimension, and your I matrix has to have the same dimensions as this, because remember, it's square, right? So if I multiply it, if this is n by m, on the right it has to be size m by m. If I multiply it on the left, okay, it has to match up with this dimension, so it's n by n. Regardless, I will get the same matrix A. Okay, so notice that I is square, but it doesn't matter what size matrix I multiply it by. Okay, so let's do an example. So let's say that we have the same matrix we had before, 1, 0, 2, 2, 1, 2. So if I multiply it on the right hand side, the dimensions have to match up, so I need a 2 by 2. If I multiply it on the left hand side, the dimensions need to match up, so I can multiply against the columns, and it should be a 3 by 3, right? So on the right side, it should be I3, and it should look like this. Zeros everywhere, except the main diagonal, which is all ones. Notice what happens when I multiply everything. I have 1, zeros times everything else, so I get a 1 here. Here I get 2, zeros everywhere else, so the second entry is a 2. Here, 0 and 0, I'm left with a 0. So I got 1, 2, and 0 so far. I multiply this times everything, 0, 0, and 1. Same thing as the last thing that stays. Okay, so far everything is matched up. Same thing here. If I multiply everything, 0, 0, and 2 on the bottom, 0, 0, and 2 on the bottom. You're going to come out with the exact same matrix that you had before. So the identity matrix is very, very important to us. Okay. If I multiply it on the right hand side, the dimensions have to match up. 1 times 1 and 0. So I'm going to get a 1 in the first position. 0 times 2 is going to be a 2, so I'm going to get a 2 in the second position. I'm going to get the exact same thing. Okay, so the identity matrix is very important because it'll commute. It's meant to, right? So here you can multiply in either way. But you're going to have to change I. It doesn't commute because you have to change the dimensions, right? So it's not the same I matrix. So properties of matrix algebra. So these are the properties that do work. So as you do math, you can use these properties. So what you're going to see is that you're going to get matrix equations, just like you would have in algebra, like 2x plus 3 equals 2 times x plus y, right? We're going to have the same sort of things here, and we're going to use these properties in order to be able to solve those kinds of things. Okay? So I need a scalar, and I need to have 3 matrices. They're going to be n by m. So remember, n and m are arbitrary. They could be the same value. These could be squares. But remember, a square matrix is a small subset of all the possibilities. So we need to keep it generalized and say that they can be any dimension. Okay? So I need 3 matrices, all the same dimension, a scalar, and our previous definitions of addition and multiplication. Okay, so we have A times B times C is going to be the same thing as if I multiply A and B first and then times C. But remember, notice I'm not changing the order in which A or B or C lie. It's still going to lie in the same order. It's just which one I multiply by first. Okay, A times B plus C. So notice that A is on the left hand side. So when I distribute this, it distributes to the left hand side. Okay, A times B plus A times C. A stays on the left side because remember, the order matters. So it would be A first and then B. If I were to distribute this on the other side, or if I swapped one of these, it would not be the same. Okay, same here. Notice that C is the one that's going to distribute across. C is on the right hand side. So when it distributes, it stays on the right hand side of the products, AC and BC. Okay. S times AB, I can take this scalar and multiply it times A first and then multiply it times B. Okay, and that's fine. Or I can multiply the scalar times B first and then multiply it times A. And that's fine as long as A and B stay on their respective sides. That's what matters. Okay. A times the identity is going to get you A. So again, notice I'm not putting the dimensions. We already talked about what the dimensions should be. This would be, on this side it would be IM, but it doesn't really matter, right? It's just the appropriate identity sized matrix for this matrix A. Okay. I times A is A. Again, this would be IN. But what matters is that it's the appropriate size in order to actually do your matrix multiplication, right? So here's our next theorem. Let A, B, and C be non-zero matrices. Okay, so they cannot be the zero matrix. Then it is possible that these two matrices commute with each other. Okay, it is possible. It's most likely that they don't commute, but they're often enough they will commute. Okay, you cannot assume that it's true, right? A times B equals 0 does not imply that A is the zero matrix or that B is the zero matrix. Okay, just because your product comes out to being all zeros does not mean one is 0. This is not regular numbers, right? These are matrices. Now, if this was x times y equals 0 and x and y were numbers, real values, yeah, one of them would have to be 0. These are matrices. It is not the same. Okay, you can multiply two non-zero matrices and get the zero matrix out. Okay, and notice again, I'm not putting the dimensions of my 0, right? It just depends on what A and B are. Okay, again, it's not necessary to put the dimensions for the i's and the 0 matrices. A times C equaling B times C does not mean that A is the same as B, or that C is the 0 matrix, making 0 and 0, or actually, you wouldn't even get 0 and 0. Well, I guess you would. But it does not mean that A and B are the same just because these two matrices are equal. Okay, so again, all the rules from regular algebra do not apply. A lot of them do, but even when they do apply, they apply with restrictions. Left and right hand multiplication are different. Okay, and then the other properties that apply from standard algebra do not always apply to matrices, right? But we do matrix algebra. Okay. Transpose, super important. We'll see it quite a bit, and as we get into the last chapter of this textbook, actually, we talk about the transpose everywhere, right? So transpose is important. The transpose of a matrix is just the swapping of the rows and the columns. So the transpose of A, the columns of A become the rows of A, of the transpose, and the rows of A become the columns of the transpose. Okay, and we call this A T, right? A to the power of T, although this is not to the power of T. T is not a number. This is just a notation. When you say A to the T, that's the transpose of A. Okay, so all you're doing is you're switching the rows and the columns. Okay, so if A is denoted as IJ, then the transpose is JI. The rows become the columns, and the columns become the rows. So an example, if this is my A, then the transpose of A means that this row becomes the first column, and the second column becomes the second row. Okay, you're basically kind of rotating it across the main diagonal 90 degrees. That's how I think about it, but it's way easier if you're just like, okay, this row is now the column, and this row is now a column, and this row is now a column, in that order. Okay, where this column is a row and this column is a row, however you want to, but the rows and columns have to swap. Okay, very important. So we have a nice theorem. If A and B are n by m matrices, C is m by k, S is a scalar, then the transpose of a sum, okay, is A transpose plus B transpose. So the transpose actually gets to distribute across this sum here. That's nice. S times A transpose is just S times A transpose. Okay. AC transpose. So here it's actually different. The order is going to switch. So you're going to get C transpose A transpose. Okay, so for a product, it does distribute, but then the order also switches. So remember, order matters, right? This is not going to be the same as A transpose C transpose. That's not going to equal here. Okay. If A is the same as its transpose, that is the definition of a symmetric matrix. Symmetric matrices are extremely important in this class. They have lots of applications in things like quantum mechanics. Okay, they're extremely useful in quantum mechanics. Actually, hear me later in the later videos. I talk about this a lot, but linear algebra is basically is just quantum mechanics. Okay, so once you learn linear algebra, if you learn the concepts of quantum mechanics, it's very easy to start to do the mathematics necessary for that. Okay. So an example. If I swap my columns and rows here, I'm going to get the exact same matrix. Okay. This column is the same as this row. This column is the same as this row. This column is the same as this row. Okay. The easiest way to understand that it's symmetric is you look at the main diagonal. The main diagonal can be whatever you want it to be. Okay. But then notice that across the entries across the diagonal are the same. 3 and 3, 2 and 2, 6 and 6. It's symmetric across the main diagonal. That's why we call it symmetric, because the transpose is just going to get you out the same thing, because you are flipping it across the main diagonal, right? And of course, it should be obvious that you can only have a square matrix be a symmetric matrix. All right, so recall that linear transformations are defined as the transformation matrix times a vector. Our transformation matrix, we're calling the matrix A. Okay, so an example. If this is my transformation defined by this, right? I plug in a two-dimensional matrix, right? In R2, I'm going to get out a matrix, I'm going to get out a vector in R2. So if I plug in a vector in R2, I get out a vector in R2 because this has two entries. But this transformation can be given to me as a matrix. If I take the coefficients and I turn them into a matrix, it's the same thing as if I say I have A times x1, right? We saw linear transformations as a matrix equation, right? As A times some input vector. In the last video, I showed you how you multiply these things together. It's the same thing as if you just take x1 and x2 and actually plug them in, right? So now we're actually looking at them as multiplications. So, quick review, right? So now let's talk about the theorem that goes with it. If S is a transformation from m dimensions to k dimensions, and T is a transformation from k dimensions to n dimensions, so notice that these inner dimensions actually match up, right? Pretty important here. So if there are linear transformations that are given by this transformation S is some transformation matrix times X, and T of Y is another transformation matrix times Y, here A has to be n by k, right? Because it goes with my T, so it's number of rows, number of columns. B has to be number of rows, number of columns. Remember, for a transformation, they're swapped around between the traditional standard rows, columns, right? It goes rows last, columns first for a transformation. Then the transformation, W of X, which is a composition where S gets plugged into T, is going to be given by A times B times X, with AB being n by m. Now, you're probably looking at this like, damn, that's a lot of stuff going on here. Like, what the hell are you doing to us, professor? Let's break it down. It's not that bad, okay? We can make this really, really simple to understand. So notice that A is n times k. So the dimensions match up. So this is what's happening. It's a composition, okay? I'm going from m to k because S is inside of T. So the first thing I do is I apply the S. I go from m to k and then from k to n, right? So my first domain is m and my ending range is n. So what I'm doing is I'm plugging one transformation into another. And so since I'm going from S first and then to T, the first transformation that has to happen is the B. And then this thing is going to be multiplied times A. So remember, left and right hand multiplication are different. It probably seems normal for you to think that you would do this first, and then multiplying that times A means that it's this thing times that. But that's not what happens. Remember how a transformation works. I'm plugging in X, so X gets multiplied on the right side, and your transformation matrix is on the left. So if I'm plugging this into this, right, if B of X is actually my Y, right, so B of X and Y are the same thing, and that means that I have Y as B of X. So that'll be A times my Y, or A times B of X. That's how you want to think about it. I'm starting in S, and then I'm ending in T. So I'm going from R to K, and then from K to N. So if S is the first thing, if S is inside of my transformation, that's the first transformation, okay? And then that transformation is multiplied times the new transformation. So that means it's this one in order of appearance, this transformation first, and this transformation, because the transformation matrices are on the left-hand side. right? So b of x gets plugged in for y. So that'll be a times b of x, a times b of x. So now what we get to do is, instead of saying, okay, let me do this one at a time by taking a specific x vector and multiplying it by b, and then taking that product and multiplying by a, I can just take my two transformation matrices and multiply them together, and then I can multiply times any x matrix that I need. Okay, so let's do an example after we look at a little bit more notation, right? So W is given by the composition of T with S, right? So T composed with S, or T of S, right? So hopefully you remember your composition notations from algebra and pre-calculus. The last one that you see is the first one to happen, or it's the one that gets plugged into the first transformation or your first function. Okay, so as far as it looks in with a graph, you start with x, you plug it into your function or your linear transformation in this case to get sent to RK, and then you take that result and you plug it into your new transformation to get to your end range. An easier way of doing that is to compose the two functions together and just plug them into one function. Okay, so I'm sure that when you first saw this, this notation is very confusing. I'm sure it's still confusing, but hopefully it makes sense to you now, the order that it's supposed to appear in. Okay, so let's do this as an example. Let my first transformation be given by the same transformation we saw earlier. Okay, and a second transformation that has this as its definition. Okay, so we need to find the transformation. So let's find a matrix A such that T1 is plugged into T2, gives a single transformation A of x. Okay, so let's think about this. This matrix is getting plugged in to this matrix. Okay, so this one is going to come first, so it'll be on the right hand side. This will be the one on the left hand side, right? Because if you come back here, from our definition, when S is first, that's the matrix that comes first, and it gets plugged in. So on the left hand side is the last one that you have. Okay, so my transformation matrix for T1 is given by this coefficient matrix. Transformation matrix for T2 is given by this. So then the order is this one first on the right hand side, and then this one last on the left hand side, right? Or this one and then this one if we're going left to right, right? So it'll be given by T2, T1, which looks like this. Okay, this one is plugged into this one, so it goes in this order, right? So when we multiply those together, this should be our end result. So this is our transformation matrix A. Okay, diagonal matrices. A diagonal matrix is very, very similar to an identity matrix in that everything is zero except for the entries along the main diagonal. And the entries along the main diagonal do not have to be 1. Okay, so diagonal matrices have entries on the main diagonal only, right? All the I terms, right, where the row and columns are the same, and zeros everywhere else. So an example, zeros everywhere except the main diagonal. Okay, so this would be a diagonal matrix. If I were to square a diagonal matrix, all I have to do is square the entries on the diagonal. Okay, same thing for any power of a diagonal matrix. This is for diagonal matrices only. Okay, if I had a regular matrix A and I wanted to square it, you do not just square every entry here. You have to multiply it by itself several times. Okay, however many times you're taking the power to. But a diagonal matrix is special in that you only have to find the powers of its actual entries. Okay, so note that this property of A to the K is only for diagonal matrices. Okay, so if I wanted a regular matrix, A squared, I gotta multiply A times A. That is not the same as 1 squared, 1 squared, 1 squared, 2 squared, right? You get something completely different when you square a non-diagonal matrix. Okay, you cannot just square everything. It does not work that way. Right? Triangular matrices, we've talked about these a little bit. They're very similar to echelon forms in that they have entries along a main diagonal and then zeros either all below or all above. Triangular matrices can only be square matrices, just like a diagonal matrix can only be a square matrix as well. Okay, you can only have square matrices be diagonal. You can only have square matrices be triangular. Okay, so we have what's called upper triangular and lower triangular. Upper triangular means that all the entries below your main diagonal are 0. It's upper triangular because that's where the values lie. Okay, so notice that main diagonal, everything below is 0. Okay, a lower triangular means that all the stuff above is 0 and you only have entries below. Okay, lower diagonal because that's where everything is. Upper diagonal because that's where everything is. Okay, everything else is 0. Elementary matrices, these are super important. We're going to talk about these quite a bit in the upcoming section. You can do some pretty cool things with elementary matrices. But right now we're just going to discuss what they are. So an elementary matrix is the matrix that you get when you do one single elementary row operation on the identity matrix. Okay, so remember we have 3 elementary row operations, which is the things from the Gauss-Jordan method. If you take your identity matrix and do just one of those, you get an elementary matrix. Okay, so let's say I take R2 and I subtract from it -2 R1. Then what I get is this resulting matrix. This is an elementary matrix because I took the identity and I did one single row operation to it. Okay, so I'm going to call that E or E1 or what have you. Okay, if A is a 3 by n, then E times A, E on the left side, will actually apply the row operation to my matrix A. So these elementary matrices are actually pretty cool because instead of doing row operations now on your regular matrix, you can do row operations on the identity, which is way easier to do, and then multiply that times your matrix to get that same result. Okay, so for instance, if this was my matrix and I wanted to add to it R2 minus 2R1, okay, that will make this 0, and that would make this -3. Okay, or I can take my elementary matrix so that the dimensions match up if I multiply and do that instead, and I will get the exact same thing. Okay, so your elementary matrices allow you to do easier single row operations on the identity, which is always way easier. Okay, because look what it's doing. It's literally telling me what I'm doing. What is R2ing? I'm taking R2 and I'm subtracting 2 of R1. Okay, and it'll do that for me. Okay, instead of doing it piece by piece, I can just say, hey, this is elementary matrix, multiply it out. So let's look at this as an example. If this is my A, okay, and then I start to do row operations, so R2 becomes R2 minus R1, so this becomes 0, -1 minus 1, so this is -2, this will be -4, right? And then I divide all of this by half, -half to make it positive, right? And then I'm done. So these are my 2 operations that I've done. Okay, the first one that I did was this one, so it would be on the left hand side. The next one I did was this one, so if I wanted to put these together, I would call this E1 and this E2. I would put them in order as E2, E1 times A. Okay, this would be my E3. So what I'm going to do is I'm going to make the value above it 0 because that is the order that we do our Gauss-Jordan elimination, right? You do your backwards phase. People in this class who are not doing it in the correct order, please start doing it in the correct order. I will be taking points off from now on. So these are my 3 elementary row operations. So let's make note of these, okay? And then let's write their corresponding matrices. It's actually very easy to write these matrices. So for the first one, okay, R2 minus R1, that should be 1, 0, 0, negative 1, 1, 0, 0, 0, 1, where it's only 2, so that's what it'll look like. Okay. Negative 1 half R2, so then that means I have 1, 0, 0, negative 1 half. Okay. And then R1 becomes R1 minus R2 will be 1 minus 1, 0, 1. It's actually very easy to create these elementary matrices. Okay, so again, remember, I'm applying these to the identity matrix. And now that I have these values, okay, it will go E3. So the last one is what's first. So you go in descending order. E3, E2, E1, and A. E3, E2, E1, and A. If I multiply these out in this order, I will get out my result. Okay, so I would start with this, and I would get that. This actually allows us to do some really cool things. Okay, so E3 was this one, E2 was this one, E1 was this one, and this was my regular A. If I multiply these out, I will get my reduced row echelon form of my original matrix A. Now we're going to do some really cool things with these in the upcoming chapters. We're going to do some decompositions, which is basically we're going to take our matrix and we're going to factor it into several products, which is a very important thing in this class. So again, you guys need to really be on top of doing your Gaussian elimination in the correct order. Okay, stop doing stuff all willy-nilly, right? So now let's talk about the last thing we're going to do, which is partitioning. We're not going to go super deep into partitioning. If you guys are into computers at all, you're going to be familiar with the idea of partitioning, although this is not the same as partitioning a hard drive. Okay. So an example, basically what we're going to do is we're going to take a large matrix and we're going to break it up into digestible pieces. Okay. So I have a 1, 2, 3, 4, 5, 6 by 5, so a 5 by 6 matrix, and I'm going to break it up into smaller sub-matrices. Okay, this is 2 by 3, 2 by 2, 2 by 1, 3 by 3, 3 by 2, 3 by 1, right? So I broke these things down into smaller pieces. And I'm going to call these each a matrix in their relative positions. So A11 is this matrix. A12 is this matrix because it's in the first row, second column, right? So the matrices are now denoted by their position in the larger partition matrix. And what I can do is I can take a second matrix and I can partition it so that it matches up, okay, dimension-wise, and I can start to multiply them together. I'm not going to do all of this work, okay, that would be left for you as an exercise, but I can actually multiply those two matrices by multiplying their respective pieces, right? I can take these rows, multiply times these columns to get the first entry. Now, in order to do that, the sub-matrices that I have also have to match up dimension-wise, okay? So now that the dimensions of each partition matrix align, such that the dimensions align to allow multiplication, and the resulting products are the same size so that they can all be added together, okay? And that's it, okay? Have a good time. See you guys next video.